Okay, so on electric forces, let's answer tutorial sheet 5, which is saying, or question 1, which is saying a small plastic sphere charged to -10 nanocoulombs is held 2.0 centimeters above a small glass bead at rest on a table. The bead has a mass of 15 milligrams and a charge of +10 nanocoulombs. Will the glass bead leap up to the plastic sphere? Will the glass bead leap up to the plastic sphere? So this is simple. We are just dealing with forces. So you have a glass bead, and you also have a plastic sphere which is charged. And if you notice, you're going to notice to say the plastic sphere and the bead that we've been given are oppositely charged, which means they are going to attract each other. So what is your job? Our job is going to be to calculate the electrostatic force, which is going to be between these two charged particles. And since they're oppositely charged, we know to say the electrostatic force will be a force of attraction. So we'll calculate the electrostatic force to see how much it is, or what is the magnitude of the force of attraction. Then we also calculate the weight of the glass bead, or rather the bead. If the weight of the bead is more than the force of attraction, which is between the two charged particles, that means it will not leap towards the plastic sphere. But if the weight of attraction is more than, or if the force of attraction is more than the weight of the glass bead, that means it is going to leap towards the negatively charged plastic sphere. So let's do this. This is question 1. This is question 1. And we've been given to say, or we know to say, using Coulomb's constant, the electrostatic force between two charged particles will be equal to K Q1 Q2 over R squared, like this. So we already know to say the value of K is 8.99 times 10 to the power 9 with units, meter, or I can say Newton, meter squared over Coulomb squared. Then we've been given the charge Q1, which I'm going to consider it as charged over the sphere. Is it the sphere? Yes, the plastic sphere, which is equal to -10 nanocoulombs. So this is the same as -10 times 10 to the power -9 coulombs, like this. Then I have my Q2, which is the charge of the bead, which is +10 nanocoulombs, and this will be equal to 10 times 10 to the power -9 coulombs, like this. What else have we been given? We've been given the distance between the two charged particles, which is 2.0 centimeters. And we're going to convert this into meters, and this will be equal to 0.02 meters, like this. Then from here, we can now plug these into the formula that we have already written here. So I'm going to say my 8, or let me write it slightly below. 8.99 times 10 to the power 9 multiplied by, what do I have? I have -10 times 10 to the power -9, like this, multiplied by 10 times 10 to the power -9 coulombs, like that, divided by the distance, which is 0.2 or 0.02. 0.02 squared, like that. So I'll plug my numerator into my calculator, and I'm getting an answer which is equal to 8.99 times 10 to the power -7 over 0 or 0.02 squared. This is giving me 4.0 times 10 to the power -4. Okay, like this. So if I plug this into my calculator, my electrostatic force is equal to 2.25 times 10 to the power 3, or to the power -3, sorry, the power -3 newtons. The power -3 newtons. So that is the electrostatic force between the bead and the charged sphere. This is the force of attraction, which is between the bead and the charged sphere. Now we can calculate the weight of the glass bead. So I know to say the weight of the glass bead will be equal to mass multiplied by gravity. So this will be equal to we've been given the mass as 15 milligrams, so we can convert this into kilograms, and we're going to get 15 times 10 to the power minus 6 kilograms multiplied by the value of gravity, which is multiplied by 9.81 meters per second squared. So this is going to give me weight, which is equal to 1.47 times 10 to the power minus 4 newtons. So this is the weight of the glass bead, whilst this is the force of attraction, which is between the two charged spheres. And if you look at this, you can tell to say the force of attraction between the two charged spheres is more or is bigger than the weight of the bead. What does that mean? That means the net force is going to be towards the charged sphere. Hence, the bead is indeed going to leap towards the charged sphere. So the answer for question 1 will be yes, the glass bead will leap up to the plastic sphere. So that is it on question 1. Let's look at question 2. Question 2 is saying two 1 kilogram masses are 1.0 meters apart, center to center, on a frictionless table. Each has a positive 10 microcoulombs, or not micro, this is millicoulombs. Each has a positive 10 millicoulombs charge. What is the magnitude of the electric force on one of the masses? And question B, what is the initial acceleration of the mass if it is released and allowed to move? So this is a very interesting question. So I've been given to say, this is now question 2. Let's say question 2. We've been given to say the masses of each block, M is 1.0 kilograms each. And they are at a distance r, which we can say is 1.0 meters, like this. Then they both have a similar charge. Can say, or I can just say Q1, which is equal to Q2, which is equal to positive 10 millicoulombs, of which if I convert this into coulombs, I'm going to get positive 10 times 10 to the power minus 3 coulombs. Then we also have our coulombs constant as usual, which is 8.99 times 10 to the power 9 newtons meter squared per coulomb squared, like that. So question A is saying we should calculate the magnitude of the electrostatic force. So the electrostatic repulsive force is the one which is going to be in action between these two objects, because both of them are positively charged. So it will be a repulsive force. So we're going to say the electrostatic force will be equal to, we already know the formula to say F is equal to K Q1 Q2 over R squared, like this. We're going to say our F is going to be equal to 8.99 times 10 to the power 9 multiplied by, in our brackets we have 10 times 10 to the power minus 3 multiplied by 10 times 10 to the power minus 3 over 1.0 squared, like this. So this is going to give us if I multiply my numerator, I'm getting 8.99 times 10 to the power minus 5, and this is going to get divided over 0.1 squared, like that. So if I divide that, I'm finding my electrostatic repulsive force as 8.99 times 10 to the power 5 newtons. That is the electrostatic repulsive force that is between the two charged bodies. Question B is saying we should find the initial acceleration of one mass. So using Newton's second law, you know to say summation of forces is equal to mass multiplied by acceleration. Therefore, our acceleration will be equal to force over mass. What force are we talking about? Is the repulsive force that is between the two charged bodies. So I'm going to say my acceleration will be equal to 8.99 times 10 to the power 5 newtons divided by the mass of the body, which is 1 kilogram. Therefore, my acceleration will be equal to 8.99 times 10 to the power 5 meters per second squared. And that, ladies and gentlemen, is the initial acceleration of one mass. That is the initial acceleration of one mass. So that is that on this particular question, which is question 2. We can now move on to question 3. So question 3 is saying what is the force F, which is the electrostatic force on the 5.0 nanocoulomb charge. What is the net, or what is the electrostatic force on the 5.0 nanocoulombs charge? So this is now the superimposed charges, where we are following the principle of superpositioning, because we have multiple charges which are exerting an electrostatic force on a particular charge. So if we look at this one, they want us to find the force F on the 5 nanocoulomb charge. Where is the 5 nanocoulomb charge? It is the one that we have here at that point. So what are we going to notice? Using the principle of superpositioning, we're going to notice to say this 10 nanocoulomb charge is going to have an electrostatic force on that particular charge, whilst even this negative 5 nanocoulomb charge is going to have an electrostatic force on that particular charge. So what are we supposed to do? We are going to find the net sum of the vectors in the x and the y axes, then use the Pythagoras theorem to find the actual magnitude of the net electrostatic force, and we can also calculate the direction of the electrostatic force. So we're going to notice to say the 5 nanocoulomb charge is a positive charge, and since it is a positive charge, that means the electrostatic force that is going to be on the 5 nanocoulomb charge due to the 10 nanocoulomb charge is going to be a repulsive force. Hence, it is going to be away from the 10 nanocoulomb charge, which means the resultant there will be in that direction. What about the electrostatic force due to the negative 5 nanocoulomb charge? This is an oppositely charged particle, so it is going to be an attractive force. That means the magnitude due to the negative 5 nanocoulomb charge will be in that direction. It will be an attractive force, so which means my two um, resultant forces due to the 10 nanocoulomb charge and the 5 nanocoulomb charge will be these ones that I've drawn in blue. So we're going to have one pointing towards the positive x-axis, whilst we have one pointing away from the 10 nanocoulomb charge. So what are we going to do first? We can calculate this distance, which is between the 10 nanocoulomb charge and the 5 nanocoulomb charge, because here we're using the principle of vectors. So I'll say I have my 0.3 there, or 0.03 meters here, 0.03 meters there, then 0.04 meters there. So I'm going to use the Pythagoras theorem. C squared is equal to a squared plus b squared to find the hypotenuse here, because this is also the same. I have 0.04 there, and I have 0.03 there. So I'm going to say my C, which is the hypotenuse, this will be equal to 0.03 squared plus 0.04 squared, like that. Therefore, my hypotenuse will be equal to, let me just plug this into my calculator. Just plug this into my calculator, and I'm getting a total distance of 0.05 meters. So that means the hypotenuse side is 0.05 meters. Now we can calculate the electrostatic force on the 5 nanocoulomb charge due to the 10 nanocoulomb charge, and the electrostatic force on the 5 nanocoulomb charge due to the negative 5 nanocoulomb charge. Okay, so we can now go to our blank board here and say this is question 3. So I'm going to say F of 10 on 5, this will be equal to K. Then I have the 10 nanocoulomb charge multiplied by the 5 nanocoulomb charge over the distance which is between the two charges. So let me now write the correct answer, or the correct values. So I have my K, which is 8.99 times 10 to the power 9, multiplied by, I have my 10 times 10 to the power minus 9 coulombs, multiplied by 5 times 10 to the power minus 9, like that, over 0.05 squared. Okay, so I'm going to get if I multiply my numerators, I'm getting, or if I multiply what I have in my absolute values, I'm having 8.99 times 10 to the power 9 multiplied by 50 by 10 to the power minus 18 over 0.0025, like that. This is going to be equal to what? Let me just plug this into my calculator. Okay, so I'm getting a total of 1.80 times 10 to the power minus 4 newtons. So this is the electrostatic force of the 10 nanocoulomb charge on the 5 nanocoulomb charge. We can now go to the next one, which is the electrostatic force of the negative 5 nanocoulomb charge on the 5 nanocoulomb charge. And as usual, this is also going to be equal to 8.99 times 10 to the power 9 multiplied by the absolute value of 5, or I can say negative 5 times 10 to the power minus 9 multiplied by the 5 times 10 to the power minus 9, like this. And this over the distance between the two charges, which is 0.03 squared, like that. Okay, so I'm going to get, if I plug in what I have, on my numerator, then divide by what I have as my denominator, I'm getting a total which is equal to 2.5 times 10 to the power minus 4 newtons. So the electrostatic force due to the negative 5 nanocoulomb charge on the 5 nanocoulomb charge is 2.5 times 10 to the power minus 4 coulombs. So this is along the positive x-axis, whilst the other one is away from the 10 nanocoulomb charge. So